Hello, my name is Yoshitomo Matsubara. We are pleased to announce that our study on symbolic regression for scientific discovery was accepted at the Journal of DMLR. We want to briefly introduce the paper through this video. This is an important study to discuss the potential of symbolic regression for scientific discovery. When we think about scientific discovery in the real world, there are various approaches. It may be a trial and error experiment by domain experts at the research labs, or use of black box machine learning models may be an option. In this study, our focus is on symbolic regression. Symbolic regression expresses the properties of data by equations and has the strength that its outputs are human interpretable. Let us give you some example. Imagine there is a tree of apples, and an apple is falling from a tree. Based on the observations, we can build a tabular datasets and treat elapsed time as an input variables and position of the apple as the target variable. The goal in this task is to rediscover a physics law from the dataset, and symbolic regression is a very reasonable choice for the task, as its solution is interpretable for humans in general. However, there are many critical issues in existing datasets and benchmark for discussing the potential of symbolic regression for scientific discovery, shortly SRSD. Let us describe the motivation and our approach to datasets in context of SRSD. Here, we highlight several critical issues in existing SR datasets. First of all, many of the popular SR datasets do not have physical meanings in the true models. Those datasets are not suitable for discussing SRSD. Even physics-inspired SR problems have many critical issues in context of SRSD. Existing SR datasets are tabular datasets with sampled values for each of the input variables, but the sampling process are oversimplified. For instance, FSRD, the Feynman Symbolic Regression database, use very narrow sampling ranges, like a uniform distribution in range of 1 to 5 for most of its SR datasets. On top of that, there are not appropriate distinction between constraints and input variables in FSRD. And the physics constants such as speed of the light are treated as input variables. It means that the physics constants are also randomly sampled from a uniform distribution, but it is not possible to observe and measure such constants in the real world. The oversimplified sampling process causes another issue: duplicate SR problems. Let's use a pair of equations from FSRD as an example. Those two equations use different symbols, but the terms in each equation are both input variables, and their values are sampled from the same distribution. Since the symbolic expressions are the same and the sampling range is the same, these two SR problems are considered identical. Approximately 25% of the SR problems in FSRD have 1 to 5 duplicates in this regard. In FSRD, there are also incorrect or inappropriate problems. Taking Bragg's law as an example, input variable for the difference in the number of the phases, n, should be integer, but sampled as a real number in FSRD. Similarly, use of arcsine, arccosine to obtain an angle variable is not experimentally meaningful for scientific discovery purpose. Lastly, existing SR datasets do not consider feature selection. When we apply symbolic regression to real-world problem, we cannot know beforehand what the variables or features should be used as part of the equation. And there is a chance that observed samples include variables that do not contribute to the target variables at all. However, existing SR datasets consists of required input variables and target variable only. Thus, those are not suitable for discussing the robustness of SR methods against dummy input variables. In this example, input variables are x0 and x1, and both the variables are used in the true models. In other words, the datasets provide only required input variables, and there should be some datasets that includes dummy input variables, like the second example. Here, x2 is a dummy variable and does not contribute to the target variable f, thus should not be used as part of the solution. In this study, we create new SRSD datasets and address those critical issues. Specifically, we redefine 120 SR problems in FSRD with carefully designed annotation policies. We started with reviewing the properties of each variable in all the problems and treated physical constant as constants in the symbolic expression. Then we redefined the sampling ranges in SI units, considering typical physics experiments for simulation. Creating 120 new SRSD datasets, we introduced 1 to 3 dummy variables with random sampling ranges to the SRSD datasets. In total, we produced 240 new SRSD datasets. Here, we introduce a few examples to highlight the difference between FSRD and our SRSD datasets. We introduced SI-derived units and SI units to this table and reconsider the properties of variables in all the equations. We intentionally sampled not only positive values, but also negative values when appropriate, treating physics constants as constants in symbolic expressions. Apparently, sampling ranges in our dataset are more practical and make the SRSD problems more challenging than FSRD. Next, let's talk about symbolic regression benchmark for scientific discovery. Same as the dataset, we rethink evaluation metrics for SRSD. In the popular symbolic regression benchmark, SR-bench, there are 3 key metrics: R-squared score-driven accuracy, solution rate, and simplicity of solution. As you can see, none of these single evaluation metrics takes into account both interpretability and structural similarity between the solution and the true models. And R-squared score-driven accuracy and the solution rate are both based on the binary evaluations. In this study, we propose a new additional evaluation metric to address these issues. And then we named the new evaluation metric normalized edit distance, shortly NED. This evaluation metric helps us discuss the structural similarity between the solution and the true model for a fine-grained analysis, rather than binary evaluation like whether or not solution completely matches the true model. We pre-process and convert a solution and a true model to skeleton equation trees. In skeleton equation, constant values are replaced with constant tokens because these values themselves do not make effect to the computation of the edit distance. Now we can compute the tree-based edit distance using Zhang and Shashar's method, and then normalize the edit distance in range of 0 to 1. Using the proposed datasets and metrics, we perform a comprehensive benchmark study and a user study. Here is the list of SR methods we consider in this study. The first 5 methods are top 5 baseline methods from SR bench in terms of solution rate for FSRD. The last 3 baselines are relatively new methods published with code following the SR bench paper. Let's start with experimental results for our SRSD-Feynman datasets. We defined 3 groups of datasets based on complexity of the problems. Overall, UDSR performed the best in terms of R-squared based accuracy, and PySR outperformed other baselines in terms of solution rate and NED. For solution rate and NED, there are still a lot of rooms for improvement that the research community can make for the challenging SRSD datasets. Now let's discuss the results when introducing dummy variables to our SRSD datasets. Note that each of the SRSD datasets have 1 to 3 dummy variables with randomly defined sampling ranges. Compared to the results in the previous slides, dummy variables damage the overall results, and we confirmed that none of the baselines methods is robust against dummy variables. We also note that the DSR may look robust against dummy variables compared to the results in the previous slide, which did not consider dummy variables. Whihowever, when we investigated how often DSR used the dummy variables as part of the solutions, the right table suggests that the DSR's use of dummy variables in solutions contributed to its improvement in R-squared based accuracy, which also suggests that R-squared based accuracy is vulnerable to dummy variables. We emphasize that this experiment also highlights that NED provides a more fine-grained analysis than the solution rate does. Since the SRSD datasets with dummy variables are more challenging, it is extremely difficult for SR methods to produce complete solutions. Since solution rates are based on binary evaluation, the solution rate rows in the left table are almost empty, while NED gives more flexibility and enables comparison across methods for even challenging problems. Okay. Besides benchmark experiments, we performed a user study to discuss how aligned with human judges the existing and the new evaluation metrics are. We first recruited 23 volunteers from industry and academia who either have doctoral degrees or are the doctoral students from diverse research domains. We asked the volunteers to assess estimated equations in the 1 to 5 scale. The higher the better. Then we computed Pearson correlation coefficients between human judges and evaluation metrics, R-squared score and NED. The table shows the correlation coefficients and the p-values. Note that NED is the lower the better. Thus, the coefficients for NED is expected to be negative. As you can see, NED has a stronger correlation with human judges than existing SR evaluation metrics, which means NED is more aligned with human judges. To conclude this talk, we want to summarize key takeaways of this study. We pointed out critical issues in existing SR datasets and benchmarks, especially when we want to discuss the potential of SR methods for scientific discovery. To address those issues, we proposed 240 new SRSD datasets and the benchmark, and performed our comprehensive benchmark study and the user study. Through the experiments, we confirmed that UDSR and PySR are new state-of-the-art for SRSD-Feynman datasets. Our user study shows that the proposed metric, normalized edit distance, is more aligned with human judges and enables a more fine-grained analysis for SRSD. We also want to emphasize that this new metric can incorporate the existing SR metrics. So we strongly recommend that the research communities use NED as an additional evaluation metrics for SRSD. We also confirmed that the dummy variables introduced to the datasets made the SRSD problems even more challenging. And the results suggest that the existing SR methods and R-squared based accuracy are vulnerable to the dummy variables. Lastly, we published our code and datasets at the GitHub and the Hugging Face. You can find more details about datasets, additional experiments, and analysis in the paper. If you find any questions about the paper, feel free to reach out to us. Thank you for watching.